Assalamu alaikum warahmatullahi wabarakatuh. This is me again, Muhammad Hayyan Al-Sibai. I was with you in the previous two videos. I gave you a quick introduction about computer systems and digital systems. This is actually part of our course, Microcontrolling Start as Professional. So today we will move to speak about some more technical issues. So in Module 2, we will focus on a little bit mathematical issues. So we'll speak today in this video in Module 2 Part 1 about number systems. Actually, it's just a quick introduction about the number systems. It's not mathematical class, so just because we are going to use these concepts in our course, we are going to give a quick introduction about them. So after completing this part or this video, you are supposed to understand the difference between decimal, hexadecimal, octal and binary numbers. Also, you understand what's called the ASCII coding. So let me start with introduction about numbers in general. So human beings start to use many types of weight for counting, so even counting by sticks, and then they move to what's called the Roman numbers. The Arabic or Indian numbers make things more easier, especially with the invention of zero. So actually the numbers, the original of Arabic or Indian numbers is the counting the numbers of angles. So as you see here, like number 1, it has 1 angle, number 2, it has 2 angles, number 3, 3 angles, number 8, 8 angles, and so on. And the oval is the 0, which means there's no angle, so 0 angles. So the concept of 0 is very important because it's like, say, reduced the big size of Roman numbers. So now we are using what's called the position value. So according to the position of the number, it has its value. So the 0 or صفر is like means empty. And one important thing is why we use the base of 10. I mean, why we count from 1 to 10, then we move to the next base. Actually, because the base 10 is related to our fingers. So like the first counting, the first human counting device was the fingers. The structure of decimal numbers is like this. When we write a number, each position of each number represents its value. In other words, we read this number as 742.45, right? So actually these numbers can be written like this. So if we start from the 2 on the left of the dot here, so as you see, we have 2 multiplied by 10 power 0. So this is position 0, plus 4 multiplied by 10 power 1. So this is position 1, and this is position 2. So here we multiply by position 2. Here position minus 1, and here position minus 2. So these numbers actually are called the coefficients. The base or radix is the 10 in the decimal system. The power is actually the position value. So this number actually, it's like 700 plus 40 plus 2 plus 0.4 plus 0.05. Taking the same concepts and changing the base, can have this different number systems, including the binary, base 2, the octal, which use base 8, the decimal that we already studied, which is using base 10, and there is what's called the hexadecimal, which is using the base of 16. So actually in this in computer systems in general, we focus on the binary, and we use octal or hexadecimal to support actually the way of representing the binary systems. So let's look at this example to understand the binary better. So for example, if in the decimal numbers, when we reach 99 and plus 1, so 99 plus 1 is 100. So what we do is we add actually 0, 0, and we move only 1 to the next position. So the next position here has 1, and here we have 0, 0. So this is read as 100. We start back at 0 again, but add 1 to the left using positional notation concept. And that is what we do in binary. So we use the same concept in binary. But the difference in binary, we don't have 9 numbers or 10 numbers like in the decimal. We have only 2 numbers, which are 0 and 1. So after 0 comes 1. After 1, we move the position to the left side and put 0. So binary has the radix of 2 or the base of 2, and it uses digits only 0 and 1 to represent the quantities. So the column weights of binary numbers are powers of 2 that is increased from right to left. So using the same, so as you see here, we have the base 2, so the position 0, 1, 2, 3, 4, and 5. So the columns weights of binary numbers are powers of 2 that increase from right to left, beginning with 2 power 0, which is equal to 1. Let's have one example. So we have 101 in binary. Actually, it's equal to 5 in decimal. How does this done? So if we take this series and we see the number 1, so it's 1 multiplied by 2 power 0. Then the number 0 here is 0 multiplied by 2 power 1 plus 1 multiplied by 2 power 2. So here we have 4 plus 0 plus 1. So the result is 5. So this is how actually basically we convert between binary to decimal. So these are like the first 16 numbers written in binary. So we can actually, this is very important because we will use them continuously, so it's better to be familiar with them. So using what's called 4 bits. So the 0 is 40, 1 is 0001, 2 is 0010, so by adding 1 each time. So 3 is 0011, and so on. We continue until we reach 1111 here. So this 1111 is representing 15. Moving to another base, the hexadecimal numbers. So actually it's like it's the same concept, but now instead of 2 numbers in binary numbers and 10 numbers in decimal, we have 16 numbers. So after we reach 9 here, we continue as A is 10, B is 11, C, D, E, F is 15. And this table actually showing you the relation between decimal, hexadecimal, and binary. So hexadecimal actually uses 16 characters to represent numbers. The numbers are between 0 and 9 are the same as decimal. Then we use the alphabeticals A, B, C, D, E, and F. Large binary number can easily be converted to hexadecimal by grouping bits 4 at time and writing the equivalent hexadecimal character. So as you see here, if we collect the 4, so this 4 can be written as 0, this 4 can be written as F. We will have more examples to understand because we are going to use the hexadecimal too much in our course actually to represent the binary numbers. So actually we use the hexadecimal to represent binary. We link them together. We will see when we have some practical explanation. Octal numbers are not used as much as the hexadecimal, but it's the same. It's using 3-bit. So now we have only 7 numbers. Okay, after 7 there's no 8. 8 is represented in octal as 10. So 1 is 9, 12 is 10, and 17 is 15. So this is also the binary, which is the same. So octal uses 8 characters as the numbers between 0 and 7 only. After 7, so 7 plus 1 is 0, 1, which is representing 8. Binary numbers can easily be converted by collecting 3. So as you see here, if we collect 3, here 3 plus 3, so 3, 1. So let's come here to make it easier. So this 0, 1, 1 is 3, and then we add 1. So here we have 3, 3, 3, which is 7, and we add 1. So this is just a quick way for converting. We will speak about this again later, as I told you. So this is basically how we represent numbers in different systems. So we will focus on binary system. I will tell you later why we use binary system, because binary system actually can be linked with electricity. Now let's move to another way of coding, which is called the ASCII. ASCII stands for the American Standard Code for Information Interchange. It's a code for alphanumerical characters and control characters, so not only A, B, C, D, also the control characters. It wasn't like invented to use in computers, it was actually invented for the telex. It's used to encode 128 characters and symbols using 7 bits, so it's 7 digits. The ASCII can be represented using the binary numbers, so using the 0 and 1. And ASCII has been suppressed by a new coding system called Unicode. So nowadays ASCII is rarely used. What we use nowadays is what's called the Unicode. So this is the table showing all the characters and how we represent them using the code. So this is the code in decimal, this is the code in binary, and this is the code in hexadecimal. So for example, the character P is like coded by 80, and this is its equivalent in binary and hexadecimal. The letter A is represented by 65. The letter A small letter is represented by 97. It's time to speak about the relation between binary system and digital electronics. So as I mentioned in module 1, in the video of module 1, digital system actually is represented by binary numerical system. We use the binary system because digital electronics circuits can represent binary symbols 0 and 1 using two levels of voltage. The positive voltage, which represent 1, and the 0 voltage, which represent 0. So most of the devices, including the microcontroller that we are studying in this course, which belong to AVR family, using the 0 volt for 0 and 5 volt, which is the positive volt for 1. Final thing to speak about is actually the data size. So as we said, like at the end, we change all our numbers using the binary, and using the ASCII, we change all our characters and even the symbols to also figures, numbers. So now these numbers are represented using registers or memory places by 0 and 1. This 0 and 1 actually are 5 volt and 0 volt. Now the unit of data is actually measured by the bit, which is 1 unit, 0 or 1. The 8-bit makes byte, okay? Now when we speak about programming or like any type of data in the memory, so like we measure them in byte. So for example, let's take C++ language if you are familiar with it. So the character is 1 byte, the integer is 4 byte, the unsigned integer and signed integer, all of them are 4 byte. So computer system is limited devices, so numbers in general are unlimited, but when we speak about computer systems, we have limitations for our numbers. That's why you see like the integer is not in, like in mathematics, the integer is unlimited, but in computer systems, if we are using 4 byte, that means we have ranges for our numbers. So I think it's enough. I stop here. Thank you for watching this video. If you are interested to know more, you can read in these references, and please watch our coming video to speak more about the digital systems, and we will speak about what's called the logic gates, which are actually the basic of any microprocessor or microcontroller. Thank you very much for watching, and see you again in the next video.